If your entire strategy in Web3 revolves around complaining about $50 transaction fees on Ethereum, you are operating on severely outdated information. In early 2026, the era of catastrophic gas fees officially died. Ethereum mainnet recently shattered its all-time high by processing 2.6 million transactions in a single day, while basic transfer fees plummeted to just 1 cent. However, just because gas is cheap does not mean it is irrelevant. Gas is the foundational economic engine of a blockchain. If you do not understand how it works, how priority fee auctions function during market panic, and why your transaction might randomly fail and burn your money anyway, you are still at a massive disadvantage. This guide breaks down the actual mechanics of network gas, the massive architectural upgrades that solve the scaling crisis in 2026, and the exact strategies professionals use to drive their operational costs as close to zero as mathematically possible. The mechanics. Why does gas exist? To understand gas, you must understand the Ethereum virtual machine, EVM, and the concept of the halting problem in computer science. A blockchain is a decentralized world computer. Every time you execute a smart contract, whether you are swapping USDC, minting an NFT, or opening a collateralized debt position, thousands of computers around the globe must simultaneously calculate the exact same math to verify your action. If this computation were free, a malicious actor could deploy a smart contract containing an infinite loop. The global network of computers would get stuck trying to solve a never-ending math problem, and the entire blockchain would instantly crash. Gas is the thermodynamic shield against this. It forces you to pay for every single computational step your transaction requires. A simple ETH transfer requires very little math, so it costs exactly 21,000 units of gas. A complex DeFi swap requires checking balances, updating liquidity curves, and routing through multiple pools, which might cost 250,000 units of gas. If your transaction runs out of the gas you allocated before the math is finished, the network instantly aborts the transaction. It throws an out-of-gas error, reverts the state of your wallet as if nothing happened. But, and this is crucial, it keeps the fee you paid. The validator still had to expend electricity to run the math up to the point of failure, and gas is how you compensate them. The math, base fees, priority fees, and the burn gas is measured in GUE, which is simply a microscopic fraction of a single Ethereum, $10 carat minus $9 ETH. Since the EIP 1559 upgrade, your total transaction cost is determined by a specific equation. Dollar total fee equals gas units times base fee plus priority fee, dollar the base fee. This is an algorithmic price set by the network itself, based entirely on real-time congestion. If blocks are full, the protocol automatically increases the base fee for the next block to deter usage. If blocks are empty, the base fee drops. The most important aspect of the base fee is that it is burned. It is permanently destroyed, effectively removing ETH from the total supply. The priority fee, the tip. This is where the actual market dynamics play out. The base fee gets your transaction into the waiting room, the mempool. But if you want a validator to actually pick up your transaction and put it into the next block, you have to bribe them. You include a priority fee paid directly to the validator. During normal network conditions in 2026, a priority fee of 0.1 GUE is enough to get your transaction confirmed in seconds. But during a market crash, when everyone is rushing to liquidate their assets at the exact same time, users will aggressively bid up the priority fee. If you don't understand how to manually adjust your priority fee during high volatility, your transaction will be stuck in the mempool for hours while the market burns down around you. The 2026 reality. Fusaka, Pure DAS, and blob space. If the fundamental math of gas hasn't changed, why did a $50 Uniswap trade in 2021 drop to $1.50 on mainnet and 1 cent on layer 2s in 2026? The answer is a multi-year roadmap of structural engineering that culminated in the late 2025 Fusaka upgrade and the deployment of Pure DAS, Peer Data Availability Sampling. Historically, the most expensive part of a transaction was not the computation, it was the storage. Layer 2 networks like Arbitrum, Base, and Optimism process millions of transactions off-chain, but they had to post all that receipt data back to the Ethereum mainnet using a highly expensive data format called call data. The Dencun upgrade, EIP 4844, introduced blob space. Instead of forcing Layer 2s to write data permanently into the core blockchain history, Ethereum created temporary sidecars of data called blobs. Blobs are massive, incredibly cheap storage spaces designed specifically for rollups, and they automatically delete themselves after a few weeks. In late 2025, the Fusaka upgrade increased the core network gas limit by 33%, while Peer DAS radically expanded the number of blobs the network could handle simultaneously. The result? The Ethereum mainnet cleared its congestion backlog permanently. Today, the mainnet operates as a high-speed settlement layer for institutions and Layer 2 aggregators. For the average retail user, the gas crisis is a historical footnote. How to reduce costs in modern DeFi? Even with structurally lower fees, professional operators do not waste capital. If you are doing high-frequency trading, compounding yield, or deploying smart contracts, you must optimize your execution. Here are the core tactics for 2026. 1. The Layer 2 default. You should almost never execute standard retail DeFi transactions on the Ethereum mainnet. The math no longer makes sense. By utilizing optimistic rollups like Base or Arbitrum, or zero-knowledge rollups like ZK-SYNC, you leverage blob space economics. A complex smart contract interaction that costs $2 on mainnet costs 2 cents on an L2. Your primary wallet activity should be entirely native to Layer 2 ecosystems, only bridging back to mainnet for cold storage settlement. 2. Intent-based trading, gasless swaps. As covered in our DEX guide, you no longer need to pay gas to trade. If you use intent-based protocols like CowSwap or Uniswap X, you do not execute the smart contract. You simply sign an off-chain cryptographic message outlining your desired trade. A decentralized network of solvers competes to find you the best price. The winning solver actually pays the network gas fee on your behalf, baking the cost into the final execution price. This entirely eliminates the risk of you paying for a failed transaction. 3. Gas limit auditing. When your wallet prompts you to sign a transaction, it automatically estimates the gas limit, the maximum amount of computational units the transaction should require. Advanced users often try to manually lower this limit to save money. Do not do this. If the smart contract requires 100,000 units of gas to finish the math, and you manually lower the limit to 90,000 to save a few cents, the transaction will mathematically fail 100% of the time. You will get an out-of-gas revert, and the network will keep the fee you paid for the 90,000 units. You can manually adjust the priority fee. The tip: but you should never manually lower the gas limit below the wallet's simulation estimate. 4. Alternative data availability, ALT-DA. If you are a developer deploying a new protocol, you are no longer restricted to paying Ethereum for data storage. In 2026, networks utilize specialized DA layers like Celestia or EigenDA. By routing your protocol's transaction receipts to these ALT-DA networks instead of Ethereum blob space, developers can drop their infrastructure operating costs by an additional 90%, savings that are passed directly down to the end user. Conclusion: gas fees are the immune system of the blockchain. They prevent spam, compensate the hardware providers securing the network, and attach a real-world economic cost to every digital